Hi everyone. So today we will discuss another chapter, which is community structure in network. Now this is a very important chapter. The reason is that community structure is one of the important properties of a network, and uh, you know, the properties like small world property, scale-free property, power law degree distribution, right, homophily, right. This property has also been rigorously studied in network science. So now this is one of the longest chapters of the book, right? So I will try to make it. I will try to present the entire chapter, part by part, right, so that you understand the concepts properly. So let's try to understand why, why community structure, what is a community, and so on and so forth. What's the utility of a community structure? So we in first chapter and second chapter, we have seen a concept called homophily, right, where we mentioned that similar kinds of nodes are attached together in a network. Say, for example, you see two friends, right, two individuals who have, say, similar background, say both both are part of same college, right, both are part of same industries. They basically become friends of each other, right? So this homophily property is something which is responsible for the formation of well connected groups, strongly connected groups. Again, I'm using the word, I'm wrongly using the word strongly connected group. Strongly connected component is not the right word, but what I'm trying to say is that because of this homophily, similar kinds of nodes, they get attached with each other and form dense groups. Okay, so it basically emphasizes this famous line that birds of a feather flock together, right? So basically, say let's assume that in a social network like Facebook, right, you see that, so say you join us, the Facebook network today, right, and you look at the other friends who you look at the other individuals who you want to make friendship with, right? So your choice might be those individuals who are basically part of your own college, for example, or those individuals who like the same kind of activities that you also like. For example, say both of you like cricket, both of you like basketball, both of you belong to the same religious group, both of you both of you have same interests, right? And you gradually become friends of each other. So this homophily property is something which is responsible for the formation of the community or the dense group, right? So what is community is not very clear, right? So community detection, that's why it is called as an ill-defined problem. It's not a well-defined problem, because the definition of community is not sacrosanct. Okay, so but roughly what people assume that communities are groups of individuals, where, I mean, in which within a group nodes are densely connected. Nodes are more densely connected within a group compared to the same across groups, right? So within a group, nodes are densely connected, and across groups, nodes are sparsely connected. But when I say that a particular group is densely connected, right? Now, what do we mean by this? How do we measure the density? So you can say that, okay, density can be measured by the total number of edges within a group divided by the possible number of edges, right? So let's assume that within a group, the edge density is 0.5, and another group, the edge density is 0.7. So how do you know which one? How do you know that, okay, this is whether group A qualifies to be a community, or group B qualifies to be a community or not, right? You don't know. So you do not know the threshold after which you say that, okay, this is a community. If the edge density is above the threshold, it's a community. If the edge density is below the threshold, it is not a community. You don't know that, right? So therefore, the definition of community is not very well defined, right? So therefore, I mean, it's good and bad at the same time. It's bad. The reason is that you need to define it, right? You also need to convince the reviewers or convince others that, okay, your definition of community makes sense. That's difficult. And the good part about it is that you can define your own way of communities and you can write papers. But of course, your task is to convince your reviewers that your definition of a community actually makes sense. Okay. So so now let's look at applications, right? Why do we really care about detecting communities? So if you know community structure well, right, it can help you predict links, predict edges in a network. How? Because let's say you have you know that you already know, let's say you already know that this is a community structure and this is another community structure, right? So you know that within a community, nodes are densely connected. Nodes should be densely connected. So as you see here in this particular community, this node and this node, these two nodes are not connected, right, at this moment. So you can say that, okay, it is highly likely that these two nodes will be connected because these two nodes are part of the same community, and being a part of the same community, it is highly likely that they should be connected because they share common properties. Okay, so community structure would help you predict links, right? We'll talk about link prediction in the next chapter, where you will see that there are many link prediction algorithms which inherently considers the underlying community structure for link prediction. Okay. Of course, it can be used for recommendation system because link prediction is nothing but a recommendation system, right? Let's assume that I hope you remember the examples of the bipartite network that I showed earlier. Say this is user and this is product, right? And you know that this user has bought these products, this user has bought this product, say for example, right? And this user has bought this product, right? And you know also that this is a community. Okay, so then it would give you an idea that, okay, since these two nodes are part of same community, they have shared interest, they have shared taste, they have common taste. Therefore, this item can be recommended to this user. This user has not bought this item yet, so this item can be recommended to this user. So it can also, so this is essentially a link prediction problem, right, in a bipartite graph setting. Okay, so information diffusion, the application I might have discussed earlier, when a particular information spreads over social network, information can be a hate speech or a fake news or any information, any message, right? Now, if you know that, okay, this information needs to be spread within a certain group, right? And you know the group from the community structure, right? Then you can appropriately spread information within the community, right? If you also say, let's say you also want to control the information diffusion, right? Now, how do we do that? So you want that your information will not move from one community to other community, right? So you know that, okay, this is a community, for example, this is another community, and these communities are sparsely connected, right? And there is a information which has been spreading within this community, and you want that this information should not move from this community to this community. Let's say there is a very sensitive information which may hurt some minority group, and this is a majority group, this is a minority group, for example. You want that this information should not move to this community. If it moves, then it may create communal riot, communal violence, right? So what you do, since you know the community structure, you try to cut these edges, or in other words, you try to incentivize these nodes, right, these gatekeepers, that look, when you get this information, please do not forward those information to the next community. Okay, you can incentivize them, you can target these nodes, you can immunize these nodes, right? And this is also important, as you understand, from the perspective of epidemic spreading, right? When you know the community structure, you want that, okay, a particular virus should not move from one community to other community. You try to vaccinate those nodes or those links, right, which basically connect the community, two communities. So therefore, community structure, the information of the community structure is very important. It can be used for strategic marketing. You remember that I mentioned about Gangnam Style, right? Why this song had become so popular. I mentioned that there must be some underlying, very intelligent marketing strategy for which most of the, it basically reached out to many individuals, right? Now, this viral marketing or targeted advertisement, this is very important, right? For example, say you do not have, let's assume that you do not have enough budget to spread certain information or to advertise your information across the whole network, right? So what you can do, you can target specific groups. For example, you target, say, you target teenagers, for example, because the product that you want to sell are basically targeted towards teenagers, right? So you can then look at communities which might represent, say, colleges or schools, right, or universities, and then you go there and advertise, right? So this is very important, that context. Community structure, knowing the information of community structure is also important to detect anomalous nodes, right? Now, what do I mean by anomalous nodes? We'll discuss anomaly detection in one of the chapters, but there are two kinds of anomalous nodes in a network. One is called anomaly with respect to the entire graph. Another is called anomaly with respect to a certain community. Okay, so let's assume that there is a right, there is a community of teenagers, okay, or there is a community of students, right, who read in class 5, for example, right? So you often see that some students who are not that meritorious, right, and their age might be higher than the average age of the other students in the class, right? And therefore that student might look like an anomaly, right, with respect to that class, right, with respect to class 5. But that student may not be an anomaly with respect to the entire school, because there might be other students of the same age who read in, say, class 10, right, or class 7, for example, right? So one is called group centric anomaly, other is called network centric anomaly, right? Both these types of anomalous nodes are difficult to detect. We'll discuss about it later. But here again, community plays a very important role, because if you do not know the community, if you do not know the community structure, you won't be able to identify the community specific anomaly. Okay. It is also important to understand the evolution of communities, right? Now, why the evolution of a community structure is important? What do you mean by evolution of a community? Say, for example, at tth time, you see that there are 3 communities in the network. At t+1 time, you see there are 4 communities, right? At t+2 time, you see there are 5 communities, right? Now, when you try to map, say, let's say there are 3 communities at timestamp t, there are 4 communities at time t+1, there are again, say, 3 communities at timestamp t+2, right? Now, if I want you to understand that, say, let's say this community, right, how this community has evolved, which one is the parent community for this community at time t, right? Whether this community has evolved from this community, or this has evolved from this, or how, right? So a community, when we look at the evolution of a community, there are different ways. One way is that a community can split, right, and then form multiple communities, right? The other possibility is that multiple communities can merge together and form a big community, right? So right, and so on and so forth. So the important research problem is, how do we understand that this is related to this community, for example. Now this is related to, for example, this community, right? This is related to this community, right? So there is something called the birth of a community, or the split of a community, the death of a community, and so on and so forth, right? Now, if you know the evolution of a community, you would be able to answer many questions. For example, in scientific network, right, Now these communities are essentially different topics. Okay, let's see that at t plus 2th time, you know that, okay, this community indicates the field, this community indicates the field NLP. Let's assume that. Okay, now if you keep track of the evolution of this community, you will see that, okay, this community has evolved from the field like AI, or the field like statistics, or the field like pattern recognition, for example, right? So over the time, papers of AI, papers of pattern recognition, papers in statistics, they basically keep they cited each other, right? And during this cross citation, for the cross citation, a new community has evolved, right? So we basically try to understand how a topic evolves over time, how a particular idea evolves over time, right? A particular language evolves over time, right? So we talk about code mixed language, right? We talk about English language, Hindi plus English, right? So if I ask you that why Hindi and English, these two languages merged together and formed a code mixed language like English, why not Hindi and Portuguese, for example? Why not Bengali or say Marathi, for example, right? So if you look at the language dynamics, how people talk to each other, right? Which kind of people talk to each other, you would see that there is a clear indication that these languages evolved because of the frequent interactions of other languages, right? Again, community structure, evolution of community structure would help you understand this kind of questions or this kind of phenomena, right? Interestingly, this is also useful in the field of criminology or detecting targeted terrorist groups, right? For example, right? So say, for example, you want to understand the spread of criminal ideology or the terrorist recruitment, right? And let's assume that you know that this is a community structure, you know that this is a network and this is one community, right? And you also know that, okay, these two nodes are criminals, right? Since this is a community structure and we know that within a community, nodes share similar interest, right? They are homogeneous in the sense, homophily, right? It is highly likely that the other two nodes, which are not marked yet as criminals, they are highly likely to be criminals, right? So you can do all sorts of funny experiments to understand the group formation in general. Okay, now what is the task of a community detection? The task of a community detection is that you are given a network like this. You see here, right? Although it's a small network, but we deal with networks with 1 billion nodes, 1 trillion nodes, for example, right? And the task is to unfold the underlying group structure, underlying community structure like this, right? You can easily see that this is impossible for a human being just to look at things manually and understand the community structure. So you have to have certain algorithms which can automatically unfold, right, the underlying community structure from a gigantic network. Okay, so I have already mentioned many applications, but again, let me reiterate again that why do we care about community structure? There are theoretical reasons, there are practical reasons. Theoretical reasons is that the community structure basically indicates different organizational units of a network. For example, say let's take a university network, right, where nodes are individuals, and if two nodes, if two individuals talk to each other quite frequently, then you can create an edge between them, right? So this is the network structure. Individuals, and if two individuals communicate with each other quite frequently, talk to each other quite frequently, you can create an edge, right? So such an individual person-person interaction network of an organization, right, of a college. Now different communities in that individual network, right, in the person-person interaction network, different communities might indicate different organizational units. For example, this community indicates, say, sports block, because here nodes are individuals who are kind of sports persons, and they meet every day, right? Therefore, they have created this dense group. This community, let's say, indicate administrative blocks, right? Where nodes are administrative staffs, and they meet regularly and they discuss, right? And so this node indicates library block, for example, right? And so on and so forth. So different organizational structure. Similar kind of structures you would see in a biological network, in a protein-protein interaction network. So they are individual, these groups may indicate something else, right? Node features, you can easily infer node features if you know the community, as I mentioned. Say, let's say that in this community, you know the node property of this, node property of this, and node property of this. You can also infer the node property of this, which is unknown to you now, right? Since you know that within a community nodes have similar properties, so it is highly likely that this node may also have similar properties that the other nodes have. Okay. Node classification problem can also be solved using community detection, because ultimately community detection or clustering is an unsupervised node classification problem. Missing link prediction, as I mentioned earlier, it can be used for link prediction as well, right? It can also be used for practical reasons. I already mentioned, for example, you can earn money if you know the community structure well. Say, right? Say, let's assume that this is a bipartite network, and you want to recommend products to users, right? You know that this is a community, right? So these 4 users, right? People, they may have same tastes, therefore they are part of the same community. Now the product ham has been bought by this user and this user, but not this user. So you can recommend this product to this user because he is also part of the same community. Okay. Similarly for other cases. So now, why community detection is a difficult problem? The reason is that apparently, if you think of the problem very carefully, this is nothing but adjusting the adjacency matrix in an appropriate manner, right? Let's assume that this is the network. There are 15 nodes, 15 or 16 nodes, 15 nodes, and you have this 15 cross 15 matrix, where if 2 nodes are connected, the entry of the adjacency matrix is 1, otherwise 0. So all these empty spaces correspond to 0 entry, 0. So these are zeros, right? So what is the task of community detection? The task of community detection is nothing but, modifying the actual adjacency matrix to a new structure, so that once all these ones basically move towards the diagonal side, right? How do we do that? You basically exchange rows and columns, right? Now remember, when you exchange 2 rows, for example, right? So here, say for example, you use the node corresponding to 4. This row corresponds to the node 4, and this row corresponds to node 9, right? You can easily swap these 2 rows, right? If you swap these 2 rows, what would happen? Nothing would change. It still indicates the same network, as if now you are denoting node 4 by node 9 and node 9 by node 4. Okay, that's all. So you can easily swap rows and columns, right? Keeping the network structure same, so that the diagonal elements, so all the ones would move to the diagonal elements, right? Now you see that in this modified adjacency matrix, right, which also indicates the same network, all the ones, most of the ones moved to the diagonal side of the matrix, and now you see blocks, different blocks of ones, right? You see all these ones, right? The first block, and this first block basically corresponds to the first community, the red community. This blue block corresponds to this community, and this block corresponds to this yellow community. Now this is a block diagonal matrix, right? A diagonal matrix where the diagonal elements form blocks, right? Now what are the other ones indicating? These other ones which are not part of any block, these ones are basically edges, right? Each one indicates an edge. These ones basically correspond to those edges which connect two communities. These are inter-community edges, right? So ones which are present, ones which are present in the blocks, in the diagonal blocks, are intra-community edges, and those ones which are not part of any blocks corresponds to inter-community edges. So community detection is nothing but a switch which basically transform an adjacency matrix to a block diagonal matrix, right? Now, given a 15 cross 15 matrix, you can judiciously, change or swap rows and columns, and you can easily get this kind of block matrix, block diagonal matrix. You do not need to do any computation as such, right? But the problem here is that this is only a 15 cross 15 matrix. It's a network of 15 size, right? Think of million cross million matrix. You can't do this manually, right? So you should have an algorithm which can automatically arrange or rearrange the adjacency matrix such that the diagonal element becomes all the ones, most of the ones clubbed together and form blocks in the diagonal part of the matrix, right? So this is the task of a community detection. Therefore, this is difficult. This is challenging, right? So now let's move to the types of communities. Okay. Roughly speaking, there are essentially 3 types of communities, but when we discuss, we say that there are 4 types of communities. Okay. Now, based on the structural properties, right? First type of community is called flat community or disjoint community. Okay. So disjoint community means those communities where a node can be a part of at most one community. Okay. A node can be a part of at most one community, right? As you see here in this network, each node is a part of only one community. Okay. Each node is a part of only one community, right? This is called disjoint community or flat community. For example, say if you consider different organizations as different communities, right, and nodes are their employees, so a person can be a full-time employee of only one organization, at most one organization. So this is a disjoint community. The second types of community is called overlapping community, where a node can be a part of multiple communities. This is natural. For example, in social network, let's assume that different fan clubs, you have Sachin Tendulkar fan club, you have A.R. Rahman's fan club, you have R.D. Burman fan club, for example, right? And you can be a part of multiple fan clubs, right? This is allowed. So overlapping community basically is more of a natural phenomena than a disjoint community. Okay. And now the problem here is that when you assign nodes when you assign each node to a community, let's say you have a disjoint community detection algorithm, right? Versus you have an overlapping community detection algorithm. In overlapping community, a node can be a part of more than one community, right? So the solution space will increase exponentially if you consider overlapping communities, because in the disjoint community, your task is to assign a node to only one of the communities. Whereas, so what you can do, you can assign this node to this community and see whether it fits well or not. Then this community, you see the fit, whether it fits well or not, and so on and so forth. In case of overlapping community, for every node, you have to do this for all the communities, and you have multiple combinations. For example, you have to see whether this node fits for A, this node fits for A or A and B, this node fits for A and B and C, this node fits for A and B and C and D, right? So you have exponential combination now. Earlier you only had to check whether this node belongs to A or B or C or D. Now you have to check whether this node belongs to A or A and B, or A and B and C, or A and B and C and D. Right? Your solution space now increases. So therefore, overlapping community detection is a difficult problem compared to decision communities. And it also, as I mentioned, it also is more natural, right? More natural phenomena than a decision community structure. Okay. The third type of community is called hierarchical community. Okay, this is again a natural phenomena happens, in most of the settings, right? So what basically it says that two nodes are connected. So it basically says that nodes form a small community, multiple small communities form a slightly bigger community, multiple bigger communities form another bigger communities, and so on and so forth. So you can basically see a hierarchical structure, hierarchical community structure, where nodes form small groups form little bigger groups form biggest group, and so on and so forth, right? And this is again natural. For example, again let's assume that in an organization, right, in an institute, right, say students in say undergrad CS form a group, undergrad ECE form a group, right, and so on. Again, all the undergrad communities form a bigger group, all the postgrad communities form a bigger group. Now the undergrad communities and the undergrad community and postgrad community, they form again a bigger level of student group, right? Now a student from one college and student from another college, right, these two bigger groups again form another bigger group, and so on and so forth, right? So this hierarchical structure is also quite relevant to the real world example, real world case. Local community is not a very it is not a type of community, but it basically says that when we talk about local community, we only look at a particular node, right? So the question that we ask here, that given a node, can you tell me that which community this node belongs to? Or given a node, can you tell me who are the other neighbors or who are the other community members of the same community where this node belongs to, right? So it basically says that given this node, I am only interested in those nodes. I am only interested in those nodes which are part of the same community where this node belongs to. That means, say for example, this node belongs to this community, right? So I am only interested in discovering this node, this node, this node, this node, and this node. I'm not interested in other nodes, right? This is called local community. So disjoint, overlapping, hierarchical communities basically deal with the entire network. Given a network, your task is to detect all types of communities, right? Your task is to group all nodes into communities, where in local community structure, given a particular node, your task is to return other community members which are part of the same community where the particular node belongs to, right? Well, you can say that why this problem is different from say a disjoint commutation problem, because a disjoint commutation problem also you detect communities, right? So this local commutation can be solved using disjoint communities. You can argue why. You can say that okay, given a network, I first discovered the disjoint communities, then I look at which community this particular node belongs to, and I return the entire community where this particular node belongs to, right? The problem, not the problem, but here the issue is that you are basically wasting your time, because you do not need to run the entire algorithm on the entire network. That would take a lot of time, right? So the cost function we'll discuss later. The cost function that is used for local community detection is very different from a global community detection, for example. Okay. So so in this particular chapter, we will mostly focus on disjoint communities and overlapping communities, and we will discuss these algorithms For decision community, we'll discuss node-centric measure, modularity, information theoretic measure, permanence, dynamic algorithm. In overlapping community, we'll discuss click percolation method, link partition, weak clamp, chain form, local expansion, and so on and so forth. I'll try to cover most of the algorithms, but may not be able to cover all. So, so the remaining algorithms which will not be covered, I would request you to look at the book. Okay, so now let's get started with the algorithm. So now we discuss that a very traditional kind of way of detecting community, more from a node-centric view. Okay, some of the terminologies that I'm going to use, sound like very ambiguous, very confusing. So that's why I'm saying that please, follow the remaining part of the lecture. So what I will discuss is that I will discuss some mechanisms, very simple mechanisms through which you can detect communities, and all of them are node-centric mechanisms. Okay. For example, I will discuss click, which we all know. Then I will try to relax the definition of click, and I will discuss something called k-click, k-clan, k-club. I will relax the definition in different ways, and I will explain something called k-plex and k-code. Okay, these definitions are ambiguous, little confusing, so therefore please be very careful. So click we all know. Click is basically a completely connected graph where all nodes are connected to all other, right? Each node is connected to all the other nodes present in the group, right? As you see here, this is a click, right? This is a click, and this is another click where all nodes are connected to each other. Therefore, the degree is 1, right? The shortest path between any pairs of node is always 1, and therefore a click is a hard definition or a strong definition of a community, right? So essentially, early days, old days, when we had the task of community detection, people used to basically detect clicks and return those clicks as communities, right? The problem is that click detection is NP complete, right? It is difficult, and the second problem is that click is a very restrictive way of defining a community, because in social network it is very less likely that within a community all the nodes are connected to each other, right? So we need to relax the definition of clickness in some ways, right? So in social network or in any other type of networks, a group looking like a click doesn't exist at all. Okay, therefore we need a relaxed definition of a click. Okay, to relax the definition of a click, people propose something called k-clicks, right? Now what is k-click? K-click is the maximal subset of vertices such that for any two nodes belonging to the subset, the shortest path distance between them should be less than equal to k. It is a subset of vertices, right? It is a subset of vertices. It is a subset of vertices such that within the subset, right? Within the subset, if you take any pair of nodes, the shortest path distance should be less than equals to k. Okay, so let's look at this network and the dotted group. Okay, this group. Okay, you see that this is a this is a 2-click, meaning that if you take any two nodes, the distance between these two nodes should be less than equal to 2, maximum 2. Okay, you take any two nodes, you take this and this, you see that the distance is 2. You take any two nodes, this and this, you see the distance is 2. You take this node and this node, distance is 1, right? This node and any node, this node and this node, distance is 2. This node and this node, distance is 2. Right? Now, here you just pause and ponder. Try to understand some of the terminologies here. I said that this is the maximal set. I hope you know the difference between maximal and maximum, right? What is maximal? What is maximum? Okay. let's assume that that you have a structure like this. Okay, you have a structure like this, and A, B, C, D, E, F, G. Okay, so let's assume that the task is to detect click. What I'm saying now, I'm explaining the difference between maximal and maximum. Maximal and maximum. Okay, right? And let's assume that the task is to detect click. Okay, task is to detect click or the maximum click. The task is to detect maximum click. Okay, so node A, B, C is a click. A, B, C is a click, but this is not a maximum. This is not a maximal click, because if you add any other node, if you add another node, and if the property still persists after adding that node, meaning if you add node D, for example, and if the resultant part A, B, C, D is still a click, then ABC is not a click. ABC is not a maximal click. What I'm saying is that, say you have a set, right? ABC is a set, right? It is not a maximal set if inclusion of another entity in that set would satisfy the same property. Okay, ABC is not a maximal set, maximal click, because if you add D, ABCD is still a maximal click. Okay, but if you take ABCD now, this is a maximal click. Why? Because if you include other nodes like E, if you include E, now the resultant part would be ABCDE. This is not a click. If you include F, this is not a click. So ABCD is the final set which you lock, which you can lock, right? Meaning that you can't add any additional element whose resultant, after addition, the resultant set is still a click. Okay, so ABCD is a maximal click. Now let's look at here. EFG is a maximal click, because if you add any other nodes into EFG, that would not be a click. So EFG is a maximal click. So this is a maximal click, this is a maximal click, right? Now what is maximum among them? The one which has largest size. So here the maximum click is this one. So a maximum click is also a maximal click, but not the other way around. Clear? So therefore, what I'm saying is that so in K click is a maximal subset of vertices such that any two nodes belonging to the subset have distance less than equals to K. Okay. So what is the problem here in this definition? This is okay, but K click has a problem. The problem here is that, as you see here, in this particular case, when I measure the distance between 3 and 5, right? I only consider this part. Okay, I only consider this part. When I measure the distance between 3 and 5, okay, I basically use the path through 4, right? I consider this path because there was no restriction in the definition that while computing the shortest path, all the nodes should also be a part of the subset. There was no such restriction. It basically said that you should have a subset of vertices, maximal subset of vertices, in which if you take any pair of nodes, the distance should be less than equals to K. Now, while calculating the distance, whether I should only consider those nodes which are part of the subset or not, that was not mentioned. So I can consider those nodes which are not part of this subset, but still contribute towards measuring the shortest path, right? So this node is not considered, right, in the maximal subset calculation. That's the problem. You should have considered this part, because shortest path, when you calculate shortest path, you should consider all nodes which are part of the set, right? So to overcome this problem, the definition of K-clan was proposed. So what is K-clan? K-clan is a stricter version of K-click, right? So what it is saying is that it is saying that only the nodes, it's a stricter version of K-click. All the restrictions which are there in K-click, like the maximality and shortest path distance should be less than equals to K. Everything is there here. All the restrictions are also here. But here it basically says that only the nodes present in the set under inspections are used to create the subgraph in which the distance between any two nodes should be less than equals to K. Meaning that you only focus on the induced subgraph of nodes present in the set, right? For example, in this particular case, in the previous case, right, when I consider these 4 nodes, these 5 nodes, I should ignore the 2 other nodes, right? So I should create an induced subgraph which looks like this. Right? And now on this, you now measure the shortest path. Right? If you measure the shortest path on this network, then you see that 3 and 5, the shortest path is 5. The shortest path distance is 3. Right? So this is not a K-clan according to the definition. Right? But if you look at this structure here, now I am focusing on this part. Earlier I focused on this part. Okay. Now my subset is this one. Okay. This is a K-clan. Because you see here is that if you take any nodes, the distance is 2. Shortest path. Right? So K-clan is a stricter version of K-click. So the maximality condition that was there in K-click is also preserved here, along with the induced subgraph condition that you consider here in measuring the shortest path distance. Right? This is K-clan. Now then people started saying that K-clan perhaps is stricter, right? You should relax it. So there is another definition called K-club. K-club is same as K-clan minus the maximality condition. So K-clan, remember, K-clan preserves all the restrictions of K-click, meaning K-clan is a maximal subset of nodes whose when you take the induced subgraph of those nodes, the shortest path distance between any pair of nodes should be less than equals to K. Right? So maximality condition, induced subgraph condition, and the distance condition in the K-clan. In K-club, we remove the maximality condition. So what I say here is that a K-club is any set, any subset of nodes, right, which once you take the induced subgraph, the distance between any 2 nodes should be less than equals to K. Right? So according to the definition, 2, 3, 4 is 2 club. Right? 3, 4, 5 is also a 2 club, because the distance is always 2, less than equals to 2. Right? This is also 2 club, but none of them are none of them are 2 clan. Remember this. Only this one is 2 clan. because the maximality condition satisfies it. Okay, so all these definitions are okay, but the problem is that they are really computationally expensive, right? Not as expensive as click detection, but still it is expensive, right? Now let's look at the other definition. Now there is something called k-plex. What is k-plex? K-plex is a subset of vertices S in a graph, right? Is called k-plex if every vertex of the induced subgraph of S has degree which is at least mod S minus k. Right? Little confusing. Let me elaborate. Okay. So let's assume that this is a network, internetwork, and let's focus on 3, 4, 5, 6, this part. Okay, this is the set S. What is the size? Size is 4, right? And let's look at the degree of each node. And when I say the degree, I only consider the induced subgraph of 3, 4, 5, 6, meaning I consider only this part. 3, right? Only the edges which are connecting nodes in this, right? So degree of each node is 3, at least 3, or at most 3, whatever, right? So right, and this is 4. So this is basically 4 minus 3 plex, 1 plex. So this is 1 plex because the node in the induced subgraph of S has degree at least 4 minus at least just a minute, at least k equals to 1, right? Yeah, so at least 4 minus 1, 3. Right, now think about it now. So as the size of the S grows, right, S grows, S is growing, okay, S is growing, right? You still have low k plex value, say k equals to 1 plex value, or 2 plex. S is growing, but still you have 2 plex. What is the meaning? The meaning is that the degree is also growing. The degree of each node is also growing. That's why each node has degree at least S minus k, S minus 1, for example, S minus 2, for example, right? So higher S value, and higher degree would indicate less k-plex value, k-plex structure. Okay. The next concept is k-core. Okay, k-core we have already discussed in the core periphery analysis. This is exactly same. So in k-core, basically the idea is that in order to detect k plus 1 core subgraph, you need to recursively remove nodes with degree k. In order to detect 2 core, for example, you need to recursively remove nodes with degree 1, meaning you first remove node with degree 1, right? That would result in some nodes with degree 1. Right? For example, at this particular stage, you see that this node has degree 1, this node has degree 1. You remove these 2 nodes. What would happen? These edges will also be removed. So in the resultant part, this node has degree 1 now. You then again remove it. Okay. So you keep on removing nodes of degree k minus 1 to obtain the k core graph. Right. So to obtain 1 core graph, you need to remove nodes with degree, recursively remove nodes with degree 0. In order to get a 2-core graph, you need to remove nodes with degree 1 and so on and so forth. So if you do that, you see here, right, all these nodes, these blue nodes should be removed to obtain a 2-core graph. Okay, then all these green nodes should be removed to obtain a 3-core graph. Okay, and so on and so forth. You remember we talked about core periphery analysis. So these blue nodes form the periphery. The next peripheral part is constituted by green nodes and so on and so forth. Right. So finding K core and K plex is also NP complete. Okay.